Well, Daniel, looks like you're the only one here. It's kind of weird. I guess I'm not sure why. It's 2:30 though. Two people. That's good.
There we go. There's a couple more.
That's good. They're drifting in. Do you go by Daniel or Dan?
I always introduced myself as Daniel, but everyone ends up calling me Dan anyway.
Oh, okay. That's probably a good sign, I guess. I know.
Yeah, it doesn't really make a difference to me. So.
All right. Yeah, with the remote, it's like you don't really get to meet anybody. So it's kind of a funny thing, but normally I kind of know everyone. But anyway, that's what we got. Fall will be different. Anyway, so I want to kind of finish up the talk on this chapter 18. I've been kind of going through this as we go along. So I started with this. It shows like when you put sulfuric acid in water, and that you get it speciates into different species, and that kind of decides. So if you're working with super concentrated sulfuric acid, it's actually not acidic, right? There's no proton, it doesn't deprotonate there. So you need to have water with sulfuric acid in order to make it acidic, right? So these kind of things, and it's a diprotic acid, so you get one, as it solvates, it first lets go of one proton, you get that HSO4 anion. Then as you increase the concentration, it releases that proton, and you get more SO4, and then as it gets to even higher concentration, you lose all the protons get eaten into the anion, and then you have no acidity, right? It's such high concentration. So it's kind of an odd, like you wouldn't expect these kind of things. If you think it's an acid, that's it. But that isn't, so it becomes even complicated. And if you look at the last example, and this is about chlorine. So if you have chlorine gas, like when you chlorinate water purification, or if you just have chlorine gas, like it's a byproduct of, in fact, the first industrial chemical is going to be brine, separating brine into HCl and NaOH. That was what Dow Chemical was formed under. So HCl, so chlorine gas is like chemical engineering's first thing, separating brine. It's basically if you have chlorine gas associated with water, it's going to go through all these different reactions. There's 5 different reactions that go on. So the vapor in equilibrium with the aqueous chlorine gas, which we studied vapor liquid equilibria, then that aqueous with water makes just HClO, an aqueous dispersion. Then you can see it goes through this like 5 different equilibrium constants involved. So that becomes really a complicated situation. So we can do that. We can solve that system in Excel, and hopefully we'll get to that. But that system can be solved in Excel using Solver to figure out. This is from a book called Handbook of Aqueous Electrolyte Thermodynamics, which is on the web page. But it's a pretty involved book. But it goes through processes. The first thing you look at is that chlorination of water issue. So they go through that in the introduction section. But he's going through like places where these electrolytes are going to be important. If you read through this, you kind of get an idea like this. To chemical engineers, this is going to be vital operation, like removing sulfur from flue gas, removing amines or nitrogen from flue gas scrubber for Cl2. If you're going through processes where we're working with salts like titania, production of TiO2 is one that I know of. You start with TiCl4 and you end up with Cl2 gas. So you have to separate it with water. So basically, or you neutralize it with an NaOH solution. So it's all electrolytes, right? And it's kind of quite complicated compared to the normal chemical reactions you look at. So immediately you walk into a chemical plant and you're going to be faced with these things that you haven't been trained in, right? So basically, it's fairly important to get an idea about this stuff. What else do you say? Any metallurgical process that involves water, corrosion, petroleum. So if you're working with brine in petroleum, like in petrochemical, wastewater treatment, and then freshwater treatment also is going to involve electrolytes, crystallization from solution. We already dealt with some problems like that. So we've kind of ignored these things, right, in a sense. So any cooling operations, the salting of the cooling water. So there's a huge number of there. I just thought it was interesting that he's got like a list of like the ones that they thought of for that book. But so this is the practice problem, is just kind of these examples, 818283, which is just plug and chug the numbers to get the melting point depression. And then this was just to go through that. Normally we're working with mole fraction, and then you can get to molarity, which is moles per liter. But actually, since moles per liter changes as the volume, as the temperature changes, then this becomes a less useful item. So you go to molality, which is moles per kilogram. Right, so normally the polyelectrolytes are dealing with molality because temperatures change, because the density changes. And then molality is just proportional to mole fraction by the molecular weight, or more or less proportional to it. Then I brought up that, like, this is acetic acid, so like vinegar, and then when it's combined with water, it deprotonates. So you get this anion and a cation, right? And you can think about that like the chemical reactions. You just have a Ka constant. That's the reaction constant for that. And then this is 10 to the minus 4.8. So log of base 10 of that minus log of base 10 of that gives you a pKa, which is 4.8, which is comparable on a pH scale. So if you're below 4.8 pH, this deprotonates, so it favors the proton part. If you're above 4.8, it forms the acid, not dissociated. So it's not acidic above 4.8, and below 4.8, it's got protons floating around, so it's acidic. Right. So this Ka minus log base 10 of the Ka gives you the pH where the thing just starts to balance out between these two. Right. It's like 50%. So that's kind of the idea of Ka. So you can map out on a diagram like where your reaction is compared to how water dissociates. So water dissociates, the Ka for water, it's a separation of H2O to H plus and OH minus. The Ka is 14. That means that the number of protons at pH 7 equals the number of hydroxyl anions. Right. So those are equal at pH 7, which is square root of 10 to the minus 14. And so log base 10 at 10 to the minus 14 gives you minus 14, and negative log base 10 gives you the pH. So pKa of water is pH. PAH, let's see, the pH is the minus log base 10 of the hydrogen ion content, the proton thing. So anyway, so that's a monoprotic acid, acetic acid, and then this succinic acid is a diprotic acid. So it's got a carboxylic acid group on each end. So it's got two acids. So that can dissociate in two steps. The first step's easier, then the second step is harder. So you have the Ka1, Ka2. So if you went from C2A, so this, to the totally deprotonated anion with -2 charge, that's going to be Ka1 times Ka2 would be the constant for that reaction. So you multiply these constants, the equilibrium constants, to get the total. So if you wanted to go from the deprotonated anion to the solid, then you'd have to have Ka2 times Ka1 to get to the aqueous, and then K solid liquid equilibria. So you'd have all those three multiplied to get this, what the reaction balance would be between the A2 minus and the solid. So these multiply, that's the point. And the other point is that equilibria happens only to the aqueous species, not to the dissociated species. So the vapor liquid equilibria you do is with this aqueous. So if it dissociates, then you're going to have less vapor pressure, right? By Raoult's law, you have less vapor pressure if you dissociate. If it's totally dissociated like HCl, there's no vapor pressure. So it just eats up all the HCl vapor, goes right into the water, almost all of it, right? Because it's totally dissociated. And same with NaOH. If you have strong acid or strong base, they're not going to have much vapor pressure, right? So in HCl, it goes to Cl2 vapor, right? So it'd be Cl2 and then to HCl, which totally dissociates. Anyway, so this is just showing, so normally we're going to be talking about the acid dissociation. So even if it's a weak base, you switch to the acid on the left and the base on the right. So I'll go through that in a minute, but basically that's how all the reactions will be based on an acid dissociation. And then it's like this, these are both written for acid dissociation. You end up with a proton over here, right? Hydrogen ion on the right-hand side. So that's an acid dissociation reaction. Right? So this is about where we were last time. So water can be, so the kind of the acid reaction for water would be water goes to OH and H plus, right? And then the other would be like H3O. So hydronium ion, which is H plus, goes to water, right? So that's kind of the reverse. That's the reverse reaction, right? So for this is defined like that's zero, because that would happen almost at a concentration of 1. Right? So log of 1, 0. And then the same here, this happens almost at a concentration of 1 for hydroxyls. So that would be like 0. But you can have other things that have a larger, like pK base or a larger pK acid, right, than water. So those things that are larger, you just call them strong acids, and the ones that are larger are called strong bases. So you could get a stronger acid if you put it in a different solvent. That's the point. You could put it in an ionic solvent that had a different pKa, and then you could shift this so you get something much stronger. So ionic fluids are used to do that. Like you can get a different solvent to use. But generally, like 99% of the time, you're talking about an aqueous solution for polyelectrolytes. This business of ionic liquids is kind of a separate subject, and almost, it's similar, but it's parallel, but it's a little bit different. So you'll use ionic liquids in batteries sometimes, but not often. Like 99% of batteries are just using water. So it's only like some kind of specialized thing. So if you have a strong acid, then it totally dissociates. Then the concentration of what you put in, the Ca, is the same as the anion concentration. Right? And the proton concentration is going to be the same as the hydroxyl concentration plus whatever these anions that come off. So you're going to have extra protons. Right? If it's a weak acid, then your pH and your concentration of protons are the same number. So this thing will follow a direct line of proportionality straight across until it gets to 7. And if it's a strong base, then the pH is going to follow a direct line of proportionality. So it'll go directly 1-to-1 through this, straight down. Right? So strong acid, strong base, it goes straight down. But if you have a weaker acid, let's see, that's not right. The strong acid, the H plus is going to be bigger than that proportionality, but the OH is going to be proportional. Sorry, this is important to get, because this is basically this ceiling chart that we have to make these, right? So it's basically you get that proportionality on the side of the weak part. Like there's a strong acid, the OH part will be parallel. In other words, 14 to 13 will be to 1, and then 14 to 12 will be to 2. So you see that line goes straight through proportionality, and then 1 to -1 will be right, and then 2 to -2 will be here. So that's the line for strong acid and strong base, right? But if it's a strong base, then then this won't be proportional, because you'll have If it's a strong acid, this thing will shift because you're going to have also these CLs. You have the OHs, and so these have to add up to 14. Like 0 plus 14 is 14. 1 plus 13 is 14. 2 plus 12 is 14. Right? Because it's 10 to the minus 14 is the Ka, and log minus log base 10 will be 14. So they have to add up to the 14 between the proton and the hydroxyl for water. But if you add in a strong acid, you also have Cl minus, so the OH is still proportional, but the H plus will shift over. It'll be a little bit higher than that line. In fact, if it's a strong acid, it'll double. So, and doubling on a log scale raises this by effect by 0.3. So if you, this is a log scale, it's log of the concentration. So the concentration doubles, it lifts this up by 0.3. So it shifts it up like just a third of the distance. Right. So you'd expect for a strong acid, the H would be shifted up by a third from a straight line, from a proportional line, and the base would still be on 14. So those two would like shift. Their intersection wouldn't be at 7 anymore. So you have minus 7 and 7 are the intersection point for just water. And that for a strong acid, that thing shifts over like a little bit, and it shifts that over. Right. So you're going to have, so you're dissociating, we'll go through this again, but you're dissociating whatever you put in. It's like acetic acid is going to have its own line here. Right, and where that line crosses, so where your H, we'll go through this in a minute. So where things cross here tell you something about what's going on. So this plot of concentration of what you put in versus pH, and they're both on a log scale. So this is minus log base 10 of the hydrogen ion concentration. Right, so they're both on a log scale, so the scales are compatible. So the crossing points are where things are equal, like where H plus is equal to whatever you put in. Right, so we'll kind of see how that works. So that tells you like the balance points if you have the equations right. So for a strong acid, you end up that this thing completely dissociates. The concentration of what you put in is Cl minus. H plus is higher. It's got Cl minus and OH minus. That means you can substitute in Cl minus for the concentration of what you put in, and you can get this equation for the proton, right? And you also have an equation for Ka, so you can write this just in terms of H plus, in terms of what you put in, right? Kind of for that equation. Then for a strong base, it completely dissociates, and it's the OH that gets shifted. So the OH is H plus Na plus, that gives NaOH, and then the concentration where you put in is a sodium ion concentration. And then you can get, you can solve for the OH concentration in that case. OH concentration will be higher, so it's going to lift to the left of the line of proportionality here. Whereas the H plus will be just, H plus is completely the concentration, so that's just the straight line. Line where minus 1 matches 1, minus 2 matches 2. So strong acid, strong base, you can tell by the shifting of these lines. So this graphical thing is just used to kind of get a rough idea of what's going on with the dissociation. So if it isn't a strong acid, so in other words, if it's in the middle of that table, so you have acetic acid is somewhere, is that the table? Is this the table? No. Yes. So you have acetic acid is in the middle, 4.756. So pH of almost 5 is where it's going to have. So pH below 5, it's going to be dissociated. Above 5, it'll be just the acid, not dissociated. So that's a weak monoprotic acid. Okay, anyway, so then you can write a more complicated balance because it's not going to be totally dissociated. So everything is a parameter in that case. So the concentration that you put in is going to be the dissociated and the associated, the sum of those two. Then you have an equilibrium constant for it, this 4.7 or minus log base 10 at 4.7. And then you have the water equilibrium constant. So you can plug these constants into these balance equations. So the charge balance, the plus has to equal the minus. And then you have this complicated balance equation when you combine these, right? So if you want to know how much of it is dissociated, so the constant from these equations, so these are the equations you'll use. So basically, how much of the undissociated acid remains? It's going to be the concentration you put in, and then the pH, then this equilibrium constant, right? So it's depending on the values of these, this thing simplifies. If you're an acidic part, and then in terms of the base that's produced, it's going to be kind of a parallel equation, right? So if you're in a basic part, this H plus, you can see this is a log scale, so this thing takes a dive. So if you're in the basic region of this, H plus is almost 0, right? So you can forget about that. In the basic part, this guy's just a constant. The same way in the acidic part, this guy ends up being a constant, because in the acidic part, H plus is way larger than Ka. So then basically this just becomes Ca, right? And this, because this is Ka divided by Ka, this is also just Ca. So in the basic part, the concentration of this is at the basically the concentration of the solution, whatever you put in. Then the acidic part, the concentration of the undissociated acid is at the concentration you put in. And then things happen at Ka. So Ka on the pH scale is kind of where you'll see things happen. So for the bases, again, you write the thing as if it was an acid, right? And then to get the base pH, you take the base pH and divide by the water pH, and you get the acid pH. So it'll be like 9.3 divided by 14 gives you whatever the acid Ka is for a base. And then you write the equation in terms of an acid, then you just use these acid equations, the same equations we just had. So for a weak base, like the acetate ion or any of these HCN phosphate, so the phosphate dissociation, right? Those are all going to be weak bases, but you'll write it in terms of a weak acid equation and use these things. So it's just one set of equations you use. So how do you do this? All right, so this is just showing how to, just a simple calculation. So there's some complicated molecule. It's going to show dissociation. It's a base. That's the equation for the base association. So it ends up, this is a base, you add water, you get hydroxyls out. So you rewrite this thing backwards as an acid equation. So you have the hydroxyl dissociated one, and then it goes back to the original molecule. So that's an acid equation. Then the base was 6.18 e to minus 13, and then you divide the water by the base, and then you get the acid, which is 0.0162. So it's less than 1, meaning that this thing is going to be a base. It's not going to, the reaction isn't going to go in that direction. So if you take a log of that, you get pKa of 1.79. So that's the point of, that's the magic point on the plot where you're going to get, well, we'll see where that magic point is later. But so anyway, if you have that Ka, then you can, from these equations, you can determine the concentration of the undissociated, and then the concentration of the dissociated at different pHs. You just plug in the pH. So the hydroxyl is going to be minus log base 10 of the pH, and then that gives you the hydroxyl, it gives you the proton concentration. You just plug that in, the concentration that you fed in. Solutions 1.5 E minus 3 molal, so that's moles per kilogram, but that is at a low concentration is the same thing as moles per liter. So then you just use that number in this equation. You get the same thing out, same units out. So basically, this is just showing you can use that. It's doing it first at pH 7, then it does it at pH 1. So at pH 7, you get none of the base, at pH 7, it totally dissociates into the base, and at pH 1.5, it's only partly dissociated. pH 1.5 is almost at this 1.79, right? So that's where you expect 50%. If you did pH 1.79, this could come out 50%. That's the idea. So it's pretty complicated. I'm hoping that doing the problems will help. Anyway, this is the Cylind diagram. So on the web page, let's go over to the web page. So the Cylind diagram, he has it in his thing. So it's called a flood diagram, but it's basically the same. I mean, it's that thing. So you can use this to do the homework, right? To find, so for the quiz, for the final, you'll have to make one of these, right? So the thing to do, if it's a monoprotic weak base or weak acid, figure out what the so it's 4.79 is the pKa. So you find that point on this. So you have the concentration that you put in. So you put in 0.01, I guess, of the this is acetic acid. So you put in 0.01 acetic acid. So that comes out log base 10 is -2. Right. So that's kind of a line in this. That's the concentration that you put in the Ca. Right. And then you put your pKa for the monoprotic dissociation and just put an X on the line there. So if you go to acidic conditions, it's going to not dissociate. So that means that it's going to just be all the original material that you put in. And then if you go to basic conditions, it's going to dissociate. So that means it's going to be all the dissociated, and it's not going to be any of the original material. Right? Because it's kind of sucking the protons off when you go to base. And then at this cross point, you find out that that's where the two will deviate. Right? And these two have to sum to the same value. In other words, that concentration is what you put in. It's going to dissociate from this to that. So the sum of those two has to be the same. So when there's none of this, that thing's all of it. When there's none of that, this thing's all of it. Right? So as you go, and this is a log scale again, right? So as you go, so you'll have, right? So again, like if it's a weak dissociation, then basically you just have pure water separating into OH and H plus. So as the acidity is 0, so it's 100% water. So at that point, this crosses there. If the acidity is 14, then you have pure base and you're here, right? And then at 7, the two are equal. So you have a straight line. These two are proportional, so you have a straight line that's going to go from 0 to 7 and 14 to 7. This is the OH concentration. That's the H H plus concentration, right? And at any given point in here, so if I go here at 8, then I have 10 to the -6, then 10 to the -8, and if you sum those, you get 14, right? So the sum of these two has to give you the equilibrium constant. The sum of the two log of the base 10 of the two concentrations has to equal -14. Right, so that these have to add up that way. And then they're equal at pH 7. And at that point, they both have 10 to the -7 molar concentration, mole per liter. So the water and the base are like that. And then you have these two acids that go to this point. And then the pH of the solution. So the acid is also, so these equations that we had, these two equations, when you get to acidic, again, this becomes like linear in the proton concentration. And when you get to the basic, this becomes linear, also becomes linear in the minus of the proton concentration, because you're dealing with a log of this thing. So log of 1 makes it negative. Right? Log of a number, inverse number, means it's a negative log. So the slope of this thing is going to be negative for the base and positive for the acid, and it's going to be a straight line. So basically at Ka, the two are equal, and there's going to be a straight line that goes to that, right? And the straight line is going to be parallel to the proton concentration. So that means that you're going to get this line is parallel to the OH, and this line is parallel to that, and they both of those lines cross at this Ka at the concentration, pKa at the concentration. So that's how this is constructed. If you just put this acetic acid into water, then the pH is going to be where H plus equals the OAC minus. So that's its natural dissociation. It's going to be a pH of like 3.2. Right, so this cross point tells you the pH of a weak acid. So that's kind of how this Cillian diagram works. I think you have to work some problems in it to figure out exactly really what's going on with this. But that's kind of the idea of this thing. So wait, that's the acid where the dissociation constant comes from. That's your pKa number. So this is just how you construct the Cillian diagram. So so this is pretty simple to do it. I mean, I think there's some homework that does this, so you can kind of figure out. So if you have a system that's polyprotic, this is just the same thing, but it's like times how many dissociations the thing has. So if you have phosphoric acid, right? It's got the first dissociation, so that's a Ka equilibrium for that. It's got the second dissociation, right? Or you could write it in terms of the phosphoric acid that you put in and dissociate to the second dissociation product, and then Ka, there would be Ka1 times Ka2, and you'd have like the proton in the original material, right? In the same way, if you go to the third dissociation or the second dissociation, then you'd end up with the third dissociation, and you end up with all three equilibrium constants to get the initial material and the final, right? And then in addition to those equilibrium balances, you have the mass balance, and there's also a charge balance for it, right? So you can kind of write this. I mean, I don't know if it simplifies it, but you can simplify it in terms of the material you put in, the C, like how much of the H3PO4 you put in originally, and then the fraction of that that's dissociated into the different parts. And in terms of these alphas, and you can write equations for the alphas, by including the mass balance and the equilibrium constants. So you get a bunch of equations. Basically, there's 5. I think you end up with 5 equations for Cl2. It looks like there's 6 here for this. You know, there's what, alpha 3, alpha 2, alpha 1. So there's 3 for this. Plus you have a mass balance and a charge balance. That makes 5. So if it's a diprotic, with a diprotic you get 5. With this it's triprotic, so you should get 6, I guess, equations. See, what you're going to do in the end is put all 6 of those equations into itself. Or first you can solve them with a Cillian diagram, depending on where you are in the thing. Or this is for chlorine gas going into water, and that can make HClO, Cl minus, ClO minus. Right, so you can have this a diprotic dissociation, plus you're starting with Cl2 vapor liquid equilibria. So these are you just plug in all, so you have the free energies for all the components. And the free energies, you can calculate the Ka just like we did with the equilibrium constant. So you calculate G using the component free energies. And then you do log of that to get Ka, right? Or exponential of that to get Ka, and then base 10 log of that to get pKa. And then once you have pKa, you can make the Cillian diagram, or you can use the Ka to calculate the moles, the mole fractions of the thing. So you have the moles. So when you minimize this, let's see. So when you minimize this, you can use solver. Okay, and you're gonna have a bunch of constraints. So the first one is D34. What's that? D34. Okay, so that's the electron balance. So you want the electrons to be zero. Like that's just the electron balance with all the species that are involved here. So each of these are a sum of the species. And you want it to balance out to zero charge. And then you're going to change the moles of everything. So all the species that are involved. So basically all these moles. And then the vapor equilibrium moles also, because it includes all the equations. So you're freely changing all the moles in this. And you're doing it in terms of these balances, like each of those equations over here in the alphas. So you balance all those equations too, and then basically you just let it run and it'll spit out like what are the moles of all the species in it. Right, so this is pretty complicated to do, but basically it's bookkeeping. It's still bookkeeping, right? So it's like taking the reaction equilibria from chapter 17 and then putting it in terms of this. The nuance to it is that the gammas from this, so the activity coefficients are calculated using, so these activity coefficients are calculated using Debye-Huckel theory. So this equation is something different than what we had before. So it involves some different parameters. But basically, it's the same idea. Like you just get a gamma and just use it to get the activity. Use the activity, the moles as the activity times the moles gives you the, or the gamma times the moles gives you the activity. Use the activity and the equilibrium constant balance, and then just then do the moles until you get the mass balances to match, the charge balances to match, and all the reaction constants to work out until the concentrations are right at whatever temperature you are. So that's kind of the goal of this chapter, is to get to that more or less. So anyway, so this is for the phosphate dissociation reaction. And it goes into all these different species. It's a tri-protonated acid, so three things can happen. So the Cillian diagram for this guy, so you can see these are listed as separate species in this chart. So you have HPO4 minus 2, H2PO4 minus 1, H3PO4. Each one has its own pKa. Right, so you have three pKa's for this guy, and then that means you're going to have three crossing points. You have like 1, 2, 3, and those three are going to be each of the three pKa's that you got. Right, and then you have the concentration that you put in. In this case, you're starting with 0.0, same thing, 0.01. 0.01 of H3PO4 put into water, then what happens to it? Like, what's the pH going to be? So you see like the H and the first dissociation cross here. That's as far as it dissociates. And the other species are almost not there. So you have just H3PO4 and H2PO4. The amount of HP4O2 is like 1, 2, 3, 4 orders of magnitude smaller. Then the amount of PO4 minus 3 is more than that. Like that's actually taking a dive. So the way this works, so if you get to so basic, it would be pure PO4 minus 3. Then that goes linear here. But once it gets to the second equilibrium constant, so once it gets to this point, the pKa of the second dissociation, this slope doubles. So that's a slope of 2 after, because it's this constant times that constant, right? So the slope here becomes 2 instead of 1. And the same thing going with the acid dissociation. It goes 1. You see it takes a turn, and then it goes to slope of 2. And this guy takes a turn and goes to 2 at that pKa. This thing is, if you figure out a couple things, you can get, this is a really complicated system. But basically, you can kind of sort out what's going on. So this Cillian diagram is actually like the only hope you have of figuring out what's going on, because otherwise it's going to be too complicated. And it gives you the answer like immediately. Like it can tell you the pH is going to be 2.8, about 2.8. It's not going to be 15, right? So if you know it's 2.8, then you can go to that Excel sheet and actually do a calculation to figure out what's going on to get the exact number. But if you have no idea, it'll be much more difficult to solve this. That's kind of the idea of this. The process is to get this diagram, work out the solution roughly, and then go to an Excel sheet and figure out what the real number is. And then you know if your answer comes out crazily different than what you got from the diagram, you know that you have to go back and do it the right way or fix the diagram. But the diagram is much easier to fix than the Excel sheet. So, so it's a mixture of phosphate and a strong acid. So you're controlling the pH with the HCl. So you're controlling the dissociation of this by adding HCl to it. And then, so basically, the proton constant, this totally dissociates. It's a strong acid, so it just makes H plus. So it just shifts the dissociation curves. Then these are just the same equations. It says there should be 6 equations here, I guess. 3 for the equilibrium constants and a charge balance and a mass balance. And so so anyway, that's kind of an example of that. So you can see, like, when you put this into Excel, they get a pH of 2.6, and we got, just from doing a diagram of that, you get roughly 2.6 out of this. You get almost the same number. Right, so that means doing the chart is a good way to go. All right, so there's that business. Then it should be folding this. Anyway, there's a lot of nuances to this. So there's a monoprotic, the diprotic. Then this is for what's called Zwitter ions. So amino acids are one kind of Zwitter ion. Zwitter ion means that it's got both an acid, it's got a carboxylic group here, and it's got a base group. So it's got these amines at the other end. So the simplest one is glycine. You see they're all the same motif, but they have a different side group hanging off. Right. So basically the simplest one is a proton hanging off. So it's got an amine and it's got a carboxylic acid. So it's got a base and an acid in the same molecule. So if you get more complicated organic molecules, there's a lot of Zwitter ions, right? Like proteins are Zwitter ions. These are amino acids, like the building block for proteins. So when you make a protein, you do a condensation reaction. This H leaves, and then it bonds, or the OH leaves and bonds with the H from the amine, and then it makes water as a byproduct, and you get kind of a bond across that. So, you know, if you're just looking at the amino acid alone, not a protein, then it will have like 2 dissociations, because it has a base that can combine with water to become a positive charged ion, like this one, or it has the acid that can dissociate and make an acid. And they have these pKa's are here, right? So it can go both to be a base or an acid, depending on what the pH is, right? And the pH in the body's 7, close to 7.4, I think. So it's basically, you want to look at these things usually in the body pH. It's going to be the same diagram. It's got the Ka's, right? The 2 dissociations. One's making OH, the other one's making H plus. So you draw the 2 lines parallel because weak dissociation. So if it's strong dissociation, this H plus line shifts. Like with the Cl plus, with the Cl2 to water, it's a strong acid, so it shifts this H plus up, right? And the OH remains the same. So basically your intersection point shifts because of that. Let's see, so 1 molar, so this capital M means molar, mole per liter. So anyway, this is a molar scale. So if it's dilute, usually you're saying that it's molal equals molar, so you can just use the same scale, but in this case, it's a little bit more concentrated. So 0.1 is kind of high. So anyway, that's going to be a line right here. And again, like the dissociation, it's below that, the equilibrium constant is going to be that concentration that you put in. And then you have the dissociated and the associated lines here, for dissociated and associated. And then the same for the second, for the base, like the H plus adding to the glycine is it over here. Right, so you can get, from this, you can get the intersection point and find the pH of it. The pH is going to be near 7 because it's a body pH is 7.4. This thing ends up being pH is 6 something. Or I guess depending on what the concentration is, I guess. Let's see, what are the two solutions on this? Zwitter Ion. I'll calculate the pH of 0.1 molar, and then what's the pH? What's the distribution at 7.4? So if you just put it in water, you get pH 6.2, like this intersection. And if you put it into 7.4, then you get these species. It's going to be mostly the amino acid, not dissociated. There's going to be 2.5 orders less of the aminated, so that the one that has H plus added, and then it's going to have like a trace amount of the one that's dissociated acid, like not even a trace amount, because that's 1, 2, 3, 4, 5, 6 orders smaller. Right? So that's almost nothing. So this is a log scale, so things really go nuts with it. Anyway, it's the same thing. You do the equilibrium equations for the two dissociations. You have the mass balance, and then you have the charge balance, like plus equals minus. So you have 4 equations. And then what you want to know is probably one. If you know do the Cillian chart first, you know what you only care about. What's the concentration of the undissociated, and then the hydroxylated one, because none of the other one, none of the protonated one. So basically, there's only going to be 2 species in the solution, and then you can solve these equations. Just plug these into Excel, put in the mass balance, put in the charge balance and the equilibria, and then put in the concentration that you put in, and then it will just solve it when you do the balances. Use solver to solve it. And so you just set that up. And it should give the same answer that you got from the Cillian chart. So buffers is another thing. So basically, if you take your weak acid and then you throw in a salt, right, then that will balance out. As it tries to deprotonate, the salt will consume the protons, and that will keep the pH constant until you consume all the salt. So you can take some acid and then put in a salt and make a buffer from that. So you have an acidic solution that's got a fixed pH. Right, and this just goes through like the balance when you have 2 components like that, how the concentration A, concentration B, and then you can balance out how the pH stays the same, as long as your concentrations A and B are the right mix. Then they can accommodate changes. It can accommodate putting in acids. So your body is basically buffered to 7.4 by the addition of weak acids and salts. So if you change the salt acid balance in your body and the pH changes from 7.4, say it goes to 7.3, you just die. Right, so basically this buffered solution is pretty vital to your longevity. So there's a lot of biology. So this chapter is like half biology, which I kind of want to just skip over because this doesn't really involve industrial chemical engineering, right? But you can look at it. It's the same topics. It's just more biological aspects of it. Isoelectric point is where this, if it's an amino acid, so this isn't, the buffer isn't an amino acid, but if you have the amino acid and it can dissociate into, can protonate or it can hydroxylate, there's a point where the charges all balance out, and it's called the isoelectric point. in the material. It's where the material doesn't have a charge. So some pH, some kind of natural pH. Silica has this in solution. Like if you make silica from solution as an isoelectric point, and the properties of it in base and acid kind of parallel each other. Like it'll precipitate on the two sides of the isoelectric point. So some salts, dissociation of salts have isoelectric points. Amino acids have isoelectric points. It's basically where the pH makes a molecule have no charge. For a molecule that can go plus and minus. But he should have put in this chapter like the silicates, which is more industrial important than amino acids. I mean, amino acids are more biology based, but I think the book is trying to go towards like biochemical engineering instead of more industrial. There's also this osmotic pressure that we talked about earlier. So this kind of membrane equilibria, we're trying to dilute the thing on the DNA is on the right side, and you're trying to dilute it by the water will try to dilute it to pump over to get, and you have a charge balance here also. So basically it's setting up equilibrium balances across a membrane, charge balance and activity coefficient balances, like chemical potential balances. There's no homework problems on that. Let's see, solubility. Redox reactions. We got a couple of minutes. We should probably talk about this. This is kind of important. So redox means you've seen it before, I think, in chemistry class, but basically electron transfers, right? So it involves ions. So it's an electrolyte issue, right? In other words, you have lithium and C6 is graphite, and then it's going to make graphite. And so the lithium goes as a sandwich between graphitic rings. That's what this LiC6 is. And this is the graphite and lithium ion, and it releases an electron when that goes on. So that's an oxidation. So oxidation is loss. It's oil. And then at the cathode, you have cobalt oxide combines with lithium ions and one electron to make lithium cobalt oxide. That's reduction because it's consuming an electron. So reduction is gain. And it's easy to remember oil rig. It's hard to remember what the G stands for. So this is the harder thing the memory trick to remember oxidation reduction. Anyway, so these reactions are going to have some equilibrium constant associated with them. They run together. So it's like dissociation, association, electrolyte balances, and then you end up with a voltage from that. This got to do with the Ka through this Faraday's constant. It's like the Ka and then the free energy. So log of Ka is going to give you the free energy of the dissociation. If you want to know the potential, this Faraday's constant will tell you the potential of the reaction. So the potential is going to be ln of Ka divided by the Faraday constant, number of electrons that transfer. And then you can tell the potential of the reaction. You can make a battery from it. Right? It'll generate electricity if you put a circuit to consume the electrons. So these are like some of the reactions you can do. Like lithium's good because first lithium's like low density, like aluminum, and it's got the highest potential for redox of all the things you could do. I mean, fluorine would be the other end. Fluorine's really dangerous, but still they use lithium fluoride. So you get the maximum juice out of it. If you add these two, you take this and subtract that one, you get the total cell potential. So if you list lithium fluoride, you have like 6 volts from the reaction for one molecule of lithium. And lithium doesn't weigh much. Which means lithium's the best thing with fluoride. Fortunately, fluoride and lithium are both toxic. Fluoride will kill you pretty fast, lithium a little bit slower. And then they're also flammable. I mean, lithium's flammable, fluorine not so much, but fluorine's more deadly. So anyway, there's a variety of things you could do to combine here, but basically those are the best, right? So to make a battery, because of the electric potential of them and the density. So it's just, yeah, so we're kind of out of time, I guess. Basically, it's like doing balances, same kind of balances to do the batteries. Hopefully you can get through the homework. And then, so it's the same thing for the homework this week. Basically, the redox stuff's in the back of the book. There's a table for the redox reactions. It's also the redox idea for biochemical systems too. And anyway, tomorrow I'll go through the problems, kind of the problems for the chapter, and then give you a hint on the what's going to be on the final. Basically, the final is going to be something like take the worst quiz that we had, like the worst performance, which is probably going to be from the first half of the class, and just kind of redo that quiz. And then this stuff will be maybe probably something like make a Cillian diagram for diprotic dissociation, then plug that into Excel and solve it. Like solve it with the Cillian diagram and solve it with the Excel spreadsheet. And then that's about what we can get out of this chapter for right now. So any questions, anything? It's okay. So thanks for sticking around. And we'll meet tomorrow and we'll go through that stuff. Thanks.